This here is problem set 28. We're going to start talking about phase diagrams. Very simply put, phase diagram is a pressure temperature plot. Okay, and most of them look something like this. Okay, and it defines where different phases are. Okay, so if you decrease the temperature a lot and increase the pressure, you're going to get a solid. If you heat something up a lot, you're going to get a gas, and between there you're going to get a liquid. And we'll use this problem set to talk about all the different properties of these phase diagrams. So list and briefly define in one sentence all possible phase changes. Okay, so we have solid to liquid is melting. Liquid to solid is freezing. Solid to gas is called sublimation. Gas to solid is called deposition. Liquid to gas is called vaporization. You also hear it called evaporation. And gas to liquid is called condensation. Those are all your possible phase changes. Alright, in the following phase diagram, what phases correspond to 1, 2, and 3? So we talked about this. Just think if I make something really, really hot, what's going to happen? I'm going to get a gas. If I make it really, really cold, I'm going to get a solid, and the liquid's going to be in the middle. What's the significance of A, B, C, and D? Okay, so let's talk about some unique ones first. D. D is called the triple point. Okay, so there's this one set of conditions, a certain pressure and a certain temperature, at which all three phases can exist. I wouldn't say that they all exist at the same time, just that all of them can exist there. C, right here, this line kind of continues. This line stops right there, and it stops at the critical point. And we'll talk about, I think, at past the critical point, if I draw lines like that, okay, this is called a supercritical fluid up here, and it called a supercritical fluid. It's where a vapor and a liquid, you can no longer tell the difference between the liquid and the gas, essentially. Okay, A, this is the line connecting a solid and a liquid, so that's a melting point. But really, this line represents a bunch of different melting points. Essentially, what's the melting temperature at this pressure? What's the melting temperature at this pressure? What's the melting temperature at this pressure? So it's not, this point A is not just a melting point. We call it the normal melting point because it's the temperature that something melts at atmospheric pressure. So if things are at normal atmospheric pressure, we call them the normal point. So in this case, melting, and in this case, this is the normal boiling point. Oops. Is B there. What do each of the lines represent? Okay, so this line here, that's going to be, right, going that way is going to be sublimation, and going that way is deposition. This line going this way is going to be melting, and that way is freezing, and here, that way is vaporization, that way is condensation, our 6 phase changes. What phase exists at the crossing of the dashed lines on the phase diagram to the right? Okay, so basically we're saying pressure of 1 atmosphere, temperature of 25 degrees Celsius. What do we get? That is a solid. What happens if you change the pressure or temperature along the dashed line in either direction? All right, well, we'll just talk about this. If I were to increase the pressure, stay solid. So nothing changes. Decrease the pressure. I'm now going solid to vapor, and that's called sublimation. Okay, what if I increase the temperature? That's going that way. Then I get same thing, sublimation. And I can also decrease the temperature, and then I get nothing. Nothing changing, I should say, in terms of phase. There we go. The image to the right is a phase diagram of an imaginary molecular compound X. Does the green line, this line, does that represent a series of freezing points, sublimation points, boiling points, or critical points? Well, this is a solid and this is a gas, so that line represents sublimation and deposition. Does the solid form of compound X float on the liquid as the liquid begins to freeze at a pressure of 300 atmospheres? Okay, so this is an interesting distinction to understand. Really what we're talking about here is, does the solid float on the liquid, or which is more dense, a solid or a liquid? Well, that's different for different compounds. So we're trying to figure out which is more dense, a solid or a liquid. Well, we've got our solid here and our liquid here. Let's think, if I have a liquid and I want to make it more dense, I'm going to take my liquid and I'm going to squeeze it, if that makes sense. I'm going to take all of my molecules, okay, and I'm going to push them together to make it more dense. Well, what does that mean? As I increase the density, what I'm doing is increasing the pressure. Well, if I'm a liquid and I increase the pressure, what happens to me? I become a solid. So in this case, the solid is more dense than the liquid. Okay, that's what this tells us, is that if I take a liquid, I increase the pressure and thus the density, I get a solid. So the solid must be more dense. And if the solid is more dense, does the solid float on the liquid? Nope, the solid sinks. And it talks about increasing at this pressure of 300. Basically what we're saying is, this is 100, 200, 300. We're basically just saying we're trying to cross the line right there. Okay, so what's the alternative? Because in this case, the solid is more liquid than the liquid. The solid is more dense than the liquid. But you'll also see curves where this melting line doesn't bend to the right; it bends to the left. And then, if I had a solid and I increase the pressure, it would become a liquid. Okay, so in this case, the liquid is more dense than the solid, and so that solid actually floats, and that's like water is a great example of that. But in this case, for this problem, the solid is more dense, and so it does not float. All right, more questions about compound X. So we're still dealing with this phase diagram up here. If sample X is left outside in a sealed container on a hot summer day, will the X in the container be a solid, liquid, or gas? Okay, left outside on a hot summer day. So hot summer day, this is Celsius, right? So I'm going to say hot summer day is about 30 degrees. Okay, and if it's outside, it's probably about 1 atmosphere, right? That's normal pressure. So that to me looks like a solid. Suppose you bring the sample of X inside and place it in an uncovered pot of boiling water on your kitchen stove. Okay, boiling water. What's the temperature at which water boils? 100 degrees. So we know it's 100 degrees Celsius, and it's an uncovered pot, so we know it's 1 atmosphere, just normal pressure. What phase change occurs, if any? So we're going from 1 atmosphere and 30 degrees to 1 atmosphere and 100 degrees. Well, what just happened? I went from solid to gas, and that's called sublimation. Another sample of X is stored in a pressurized container, pressure 50, in a freezer at 0 degrees. If the sample then is then transferred to an oven and slowly warmed to 50 degrees, what phase change happens? Okay, so we're starting at 50 atmospheres and 0 degrees, and then going up to 250 degrees. So pick a different color. So we're starting at 50 atmospheres, which is 10, 20, 30, 40, 50. 50 atmospheres and 0 degrees right here. up to 250 degrees. Okay, so we melt and then we vaporize because I crossed the solid liquid line and I crossed the liquid gas line. There we go. So hopefully that's given you a good idea of how we can use these graphs, what type of questions we can ask you. All right, to the right is a phase diagram of water. So this we talked about water. This line bends to the left instead of bending to the right. It has a negative slope instead of a positive slope. All right, label each region with the appropriate phase. Okay, again, if I increase my temperature a lot, I'm going to get a gas. If I decrease my temperature a lot, I'm going to get a solid. And in the middle, I'm going to have liquid. As you go deeper in the ocean, the water gets colder, eventually reaching 0 degrees. Why do you not observe ice in the ocean? Basically, we're saying at the very bottom of the ocean, it's less than 0 degrees Celsius. But at 0 degrees Celsius, water's supposed to freeze. So why don't we see that freezing? Well, it gives you a hint here. The fact that the pressure at the bottom of the ocean is about 1,000 times greater than at sea level. So if sea level is 1 atmosphere, pressure at the bottom of the ocean is way up here somewhere, at like 1,000 atmospheres. Well, if you notice this line goes to the left, and so at 1,000 atmospheres, this line could be way over here. You're way off the graph. And at 0 degrees and 1,000 atmospheres, am I going to be a solid? No, I'm still in the liquid phase because the melting line of water goes up and to the left. So I'm going to say at high pressures, water's melting point decreases to below 0 degrees Celsius. And therefore, really high pressure at the bottom of the ocean doesn't matter that it's super cold because that increased pressure will keep it a liquid. All right, use a phase diagram of water in the previous problem for the following. Okay, so we're using the same phase diagram. Erase this stuff. Okay. Label points A through E. A. Okay, if I had to guess, A was probably representing the triple point. B is the critical point. C is normal. Melting point. D is the normal boiling point. And E, I'm not totally sure what E is representing. I'm guessing it's just talking about this whole line. So let's just call it sublimation. We'll call it the sublimation line. Okay. Freeze drying is used to preserve food at a low temperature with minimal loss of flavor. It's accomplished by freezing the food and then lowering the pressure with a vacuum pump to sublime the ice. Must the pressure be lower than the pressure at the triple point of water? Okay, so let's look at this. So we're going to freeze the food. So we're going to take our food. It's got some ice in it, or it's got some water in it. We're going to freeze it. So all of that water turns to ice in the food. Freeze the food. And then lower the pressure with a vacuum pump to sublime the ice. So then we're going to take it, use a different color. So we're going to say we start here. We're going to freeze the food and then lower the pressure. Bad line. Lower the pressure. Because if you notice here, what is this going to do to all the water in the food? It's going to take it from being ice and then it's going to sublime straight into vapor. You're not going to get any liquid water. It's because we went straight from solid to gas. Must the pressure be lower than the pressure at the triple point? So here's the pressure at the triple point. If we want to sublime it, we've got to cross this red line, which means we're definitely going to have this pressure on the y-axis. We're definitely going to have the pressure lower. Yes. Okay, that's number 7. Number 8. The melting point of solid hydrogen is 15 K at 1 atmosphere. The temperature of the triple point is 13.8 K and that many atmospheres. Does H2 expand or contract when it freezes? Okay, so remember, expansion or contraction depends on whether this melting line goes this way or this way. That's what we're trying to figure out in this problem. And they give us enough information that we can sketch out a little phase diagram for this guy and see what we get. So we know pressure is going to be here, temperature is going to be here, okay, and then so let's just, we know we're going to, the lowest temperature we've got is this guy. So this is the triple point, is at, I'm just going to say right here is going to be 0.0695. Oh, nope. Sorry, this is 13.8 Kelvin. And then here we have this line is 0.0695 atmospheres. Well, then we know the melting point. So the melting point's on this upward line, right? It's at 15 Kelvin and 1 atmosphere. So like right here, which means this melting point, or this melting line, must go up and to the left, because at a higher pressure, you've got a higher temperature. Or sorry, up and to the right. Wow. If I wanted to go up and to the left, at a higher pressure, I would need to be a lower temperature than the triple point. So this graph is going to have some boiling line there. But here, if that's my liquid, that's my solid, that's my gas, when it freezes, if I have a liquid, if I want to make it freeze, I need to increase the pressure. So the solid is going to be more contracted than, the solid is going to be more dense than the liquid. And so when it freezes, it contracts because of the slope of that melting line. And then our last one here, sketch the phase diagram for material Z. Gives us a triple point, a boiling point, and the normal melting point. So we know the general shape, pressure, temperature. Triple point is 152 Kelvin and 0.371 atmospheres. We know it's going to connect from that 0 point. There's our sublimation line. Then boiling. So boiling is going to be along this line, right? At 1 bar. 1 bar is very close to 1 atmosphere. So I'm just going to put 1 atmosphere. We have a boiling point of 166 Kelvin. So this line right here. And then a normal melting point, so again 1 bar, 1 atmosphere, is 161 Kelvin. There we go, that's my solid, my liquid, and my gas. There we have it, there's our phase diagram for material Z. All right, so hopefully phase diagrams are relatively straightforward, and hopefully this gave you an idea of the type of questions that we can ask you about phase diagrams and interpreting them.